Right at the heart of all this incredible tech we use every day, there's this huge tension. On one side, you've got the insane power of AI. On the other, our basic right to privacy. And the big question is, can we actually have both? Let's dig in.
So every time you interact with a large language model, whether you're asking it a question or getting help with an email, you're plugging into this massive brain that's been trained on just an unimaginable amount of data. But there's a little something about how these models learn that maybe you don't know about.
And that's the secret, right? What if somewhere inside that ocean of training data was your stuff? A private email, a confidential document from work, maybe even a health record. And what if the AI didn't just learn general ideas from it, but it actually memorized it word for word, ready to spit it back out to someone else?
Yeah, this brings us to a really serious issue that researchers have been wrestling with for years. It's what we call AI's hidden memory problem.
And this is not some sci-fi what-if scenario. It's a real thing called training data extraction. If your personal, private information happens to be in the training set, the model can accidentally just leak it. And that's the whole issue right there. This hidden memory completely shatters the trust we need to place in these amazing tools.
So what do we do? Is there a solution? What if you could build an AI that had a kind of engineered amnesia, where it just couldn't remember the specifics? What if there was a mathematical guarantee that it couldn't leak your private info? Well, it turns out there is.
It's a concept called differential privacy, or DP for short. Honestly, the best way to picture it is like this. While the AI is learning, you very carefully inject a little bit of random noise into the process. It's just enough static to make any one person's data impossible to pick out, but it's not so much that it stops the model from learning the big, important patterns from the whole group. It's not just a good idea, it's a formal mathematical promise of privacy.
Sounds pretty great, right? Well, there's always a catch. And historically, that promise of privacy has come with a really steep price tag. And here it is. This is the trade-off that has just plagued this field for years. On one hand, you have standard training. It's fast, efficient, and gives you these super high-performance models. But when you try to train with differential privacy, it's a whole different story. It has always been incredibly expensive to compute, and that noise we added to protect privacy, it usually tanked the model's performance. This created what everyone calls the utility gap. Basically, you got your privacy, but you lost a whole lot of usefulness.
For the longest time, that tough trade-off just seemed like the cost of admission if you wanted privacy. But some really recent research from Google is completely rewriting the rules. They've come up with what is essentially a new blueprint for building private AI without those crippling downsides.
The researchers figured out what they call scaling laws for differential privacy. The easiest way to think about it is like a recipe book for AI. It gives you this precise set of rules that tells you exactly how to balance all the ingredients, like the model size, your privacy settings, and your budget for computing power to bake the best possible private AI. It takes all the guesswork out of it.
And get this, one of their biggest findings was totally backwards from what everyone assumed. To build the absolute best private model, you don't go bigger. You actually need to use a smaller model, but train it using a much larger batch size, which is just the chunk of data the model looks at in one go. This discovery completely flips the old way of thinking on its head.
All right, so with this brand new blueprint in hand, the researchers decided to build something totally new, from the ground up, a model that was designed from its very first line of code to be both powerful and private.
So, meet Vault Gemma. It's a new open model with 1 billion parameters. You can just think of parameters as the little knobs the AI turns to learn, and the really special thing about it is that it was trained entirely from scratch with differential privacy, using those new scaling laws as its instruction manual.
So how good is it? Well, if we look at this reasoning test, the non-private version, Gemma 3, definitely scores higher. That utility gap we talked about, it hasn't completely disappeared. But, and this is the amazing part, look at its score compared to GPT-2, a really powerful non-private model from just 5 years ago. VaultGemma is right there, playing in the same league. This is huge. It proves we can now build private models that are just as capable as the non-private, top-of-the-line models from the very recent past.
Okay, so the performance is clearly there. That's impressive. But that brings us right back to the most important question of all. Did it actually solve that hidden memory problem?
Zero. Zilch. The researchers threw everything they had at this model, trying to trick it into spitting out bits of its training data. And the result? Zero detectable memorization. Not exact matches, not even close matches. The differential privacy did its job perfectly.
This is so much bigger than just one cool new model. This is really a proof of concept.
It signals a fundamental shift in how we can think about building artificial intelligence from now on.
And this just blows the doors open for so many real-world uses. It means a company working in healthcare or finance could fine-tune a model on its own super-sensitive data and actually be confident that it's safe. It lets us build creative tools and chatbots that have privacy baked right in from the start, not just tacked on as an afterthought.
At the end of the day, Vault Gemma and these new scaling laws give us a clear roadmap to the future. They show us that we don't actually have to choose between powerful AI and our own privacy. We can, in fact, engineer these systems to have both right from the start, by design.
And that leaves us with a pretty fascinating question to chew on. As this technology gets even better, and as that utility gap keeps shrinking, are we heading for a future where building an AI that isn't private by design just becomes unacceptable? Could this become the new standard for everything? Now that is definitely something to think about.